So the idea with these variances is the bigger the number, the more spread out these values are. The smaller the number, the less spread out these values are. Here's the variance of the population. Here's the variance of the sample means that we'd get if we repeatedly drew samples from that population. This is this same quantity divided by some number, right? If n is equal to 100, then sigma squared over n is certainly a smaller number than sigma squared. And note that the bigger the sample size, the bigger the number we divide by here, the smaller this variance is going to be. And there should be some intuition behind that. Suppose that I'm only sampling 3 women from the population and writing down the mean of their heights. I wouldn't be completely shocked if I sampled 3 women from the population and the average of their heights was 5'1". That wouldn't shock me. But if I sampled 10,000 women from the population and the average of their heights was 5'1", that would surprise me. Why didn't I get more tall women in that sample of 10,000? The variance of the sample means, in other words, the precision of my estimate. This is the same concept we've been talking about, the saltiness of the soup, the precision of my estimate of how many voters in California are going to vote for the Democrat. Depends on the sample size, depends on how many units, how many people we choose from the population. There's no number in here representing how many women are in the total population. That's not part of the calculation. But the sample size, the number of women we select from that population, is part of this calculation. The bigger this lowercase n, the bigger our sample size, the less we expect the sample means to vary. In other words, the closer we expect the sample means to be to the middle value.